Hi, my name's Tom Dick. I'm a mathematics professor and a math advisor for Texas Instruments. This video is part of the TI-Nfocus AP Calculus series. We're going to take a look at the topic of particle motion along a coordinate axis, using the TI-Nspire to visualize the velocity and acceleration. We're going to use as examples two moving particles that were featured in free response question number 2 off the Release 2021 AP/AB exam. Let's take another look at that question. Particle P has an initial position on the x-axis at time t equals 0, 5, and this given velocity function, which we've labeled Vp of t, for the time interval 0 to pi. Particle Q, a second particle, has an initial position of 10 at time t equals 0, and this velocity function that we've labeled Vq of t over that same time interval. Part A of the question asks to find the positions of particles P and Q at time t equal 1. Part B of this question then asked if particles P and Q were moving toward each other or away from each other at time t equal 1. And then you were also asked to explain the reasoning. Part C asked for the acceleration of particle Q at time t equal 1 and whether the speed of that particle was increasing or decreasing at that time. Finally, Part D asked for the total distance traveled by particle P over the entire time interval from 0 to pi. Now, Steve Kokoska has produced a video where he goes into detail the use of the TI-Nspire to calculate the answers to each of these questions. And so we're not going to duplicate that here. Instead, what we'll be doing is using the TI-Nspire to provide kind of a special visualization tool for investigating particle motion. So on the next page of this document, which is provided also as a resource, we're going to define the given velocity functions for these two particles. And then we're also going to define the corresponding acceleration functions and position functions for the two particles. That gets us set up for the next page of the document, which provides the punchline. And that's this interactive visualization tool where we'll have a slider that lets us control the time, and it will display the position, velocity, and acceleration of these two particles, both numerically and graphically. Okay, so here are our definitions. So you can see at the top, these were just simply the two velocity functions for the particles P and Q respectively that were given to us in the problem. So we've defined those. Now to get the acceleration functions for the two particles, which we've labeled AP and AQ of t, we simply differentiate the corresponding velocity functions Vp and Vq. And finally, to get the position functions, xp and xq, we use the initial position of each particle, and then we add on a definite integral function from 0 to t of the velocity function for that particle. So that's giving us the initial position plus the change in position up until time t, which will give us the current position of the particle. So we define that for particle P, and then xq of t gives us the initial position of 10 plus the change in position definite integral, which will provide the position of particle Q at time t. So we have our position, velocity, and acceleration functions all set up, and we're ready to move to the visualization. Let's take a look. Okay, so here we have a coordinate axis, and you can see points P and Q on that axis. Point P is at its initial position of 5, Q is at its initial position at 10, and up here we have a slider which will allow us to increment time from that starting value of t equals 0 through the time interval from 0 to pi. Now down here at the bottom we have numerical displays for the current position at the current time readout for particles P and Q. Those are in blue. In green here we have the velocities of the two particles, and in magenta we have the accelerations of the two particles. Now notice that the acceleration and velocity for particle P at time 0 happens to be 0. And that's why you're not seeing any kind of visual display corresponding to velocity and acceleration for point P. But point Q has a velocity of negative 1.8, and that's being pictured or illustrated by a vector that's pointing to the left with a length of 1.8. Similarly, to visualize the acceleration, you see this vector of length close to 0.6 pointing to the right, representing that positive acceleration. As we increment time, I've incremented it by 1/10 of a time unit. Now we can see that those have been dynamically updated. The numerical displays have changed. We now have a very small but positive velocity for particle P, a little bit in a positive acceleration. The velocity for particle Q still negative, but it's a little bit shorter in length than it was before. Now as we increment time through the time interval with increment steps of 0.1, you can actually see both the numerical and visual displays of the velocity and acceleration, as well as the movement of the particles themselves along the x-axis. Now at time t=1, recall that we're asked if particles P and Q are moving toward each other or away from each other at that time. Now we can see particle P is definitely to the left of particle Q, but it's the velocity vectors we want to take a close look at. Because they're pointing toward each other, that's indicating to us that P and Q are indeed moving toward each other. Now, I noticed that the velocity for particle Q is exactly -1. Well, let's see, take a look. If we put in 1 in for t, we'll get -0.8 times 1.25. If I calculate that out, it will be exactly -1. So that makes sense. A little bit of a numerical reality check here. Let's go ahead and increment time values further. We can see that points P and Q continue to move toward each other. But I can see here sometime between 1.3 and 1.4 for time, we've got a change in the sign of the acceleration vector for particle P. And it's now pointing in the opposite direction, which means particle P will be slowing down. It's still moving to the right. You can see that that acceleration vector is getting larger and larger in the negative direction. At 1.8, that makes sense. Remember that factor of t minus 1.8 in the expression for the velocity function for Q. Makes sense that would be 0. As we continue to increment, we now have particle Q has turned around. It's now moving to the right. And we increment just one more. Now we have particle P is moving to the left, particle Q is moving to the right, which means now the two particles are moving away from each other. And we continue to increment time through the time interval, and P and Q continue to move away from each other. And let's see, we'll get up to 3.1. Let's see, since pi was 3.14, that'll be all we can do. Let's go ahead and initialize back to time t=0. And what I'd like to do is get a sense of the path of the particles. And to do that, I'm going to make use of something called the geometry trace. So I pull up the trace menu in geometry trace, and I'm going to select points P and Q. What's going to happen is as I increment time now, the points P and Q are going to leave behind a trail of the positions that they have occupied. So you can see as I increment time t here, we're seeing this trail of points that P and Q are leaving. It gives us a sense of the path or trajectory of the two particles as the time has elapsed through this time interval. Here we can see how now the points P and Q have turned around and are now tracing back over positions they've already occupied. And that helps us get a sense of the difference between displacement or change in position and total distance traveled. Okay, well that winds up this video. For more resources like these, please go to education.ti.com.